Welcome to The Explainer. Today, we're zooming in on something unbelievably small, yet incredibly powerful, the atomic nucleus. You might think of atoms as these static little building blocks, but at the nuclear level, it's actually a microscopic battleground. Forces are just constantly fighting for dominance, and the ultimate prize is stability. So, in this explainer, we're going to decode the fascinating rules of nuclear chemistry.
Here's our roadmap for today. 1. Inside the atomic nucleus. 2. Mass defect and binding energy. 3. The band of stability. 4. Particles and nuclear equations. 5. Modes of radioactive decay. And finally, 6. Transmutation and nuclear energy.
Section 1. Inside the atomic nucleus, the microscopic battleground.
Okay, let's dive into this. To really grasp nuclear chemistry, we have to understand the extreme environment we're dealing with here. Protons and neutrons, collectively known as nucleons, are packed together so tightly that it frankly defies our everyday understanding of matter. The nucleus has a radius of about 10 to the negative 15 meters. It's unbelievably dense. Just to put that into perspective, Earth's actual radius is roughly 6.4 million meters. But if the Earth were made of matter as dense as an atomic nucleus, its radius would be only 200 meters. You could literally walk across the entire planet in a few minutes. That is how absurdly close these subatomic particles are packed together.
But wait, there's a massive problem with this setup. Protons are positively charged, right? And as we all know, like charges repel each other. Packing all these positive charges into such a tiny, dense volume should cause the nucleus to just instantly blow itself apart due to that intense electrostatic repulsion. So why doesn't it? Well, the answer is the strong nuclear force. This is a powerful, very short-range, attractive force that acts between protons, between neutrons, and between protons and neutrons. Over tiny distances, we're talking less than 10 to the negative 15 meters. This strong force is vastly more powerful than the electrostatic repulsion trying to push everything apart. It's literally the superglue holding the universe's building blocks together.
Section 2. Mass defect and binding energy, the ultimate power.
To really see the ultimate power of that strong nuclear force, we have to look at what happens when a nucleus actually forms. It's wild. If you calculate the mass of the individual protons, neutrons, and electrons that make up an atom, and then compare it to the actual experimentally measured mass of that assembled atom, you'll find a discrepancy, a literal cosmic accounting error. The assembled atom actually weighs slightly less than its individual parts. We call this difference the mass defect. But, mass doesn't just vanish into thin air. As Albert Einstein famously showed us with E equals mc squared, that missing mass has been converted directly into energy, specifically nuclear binding energy. That's the energy produced when the nucleons bind together, and it's the exact same amount of energy you'd need to blast them apart again. Let's compare the sheer scale of this energy for a second. In everyday chemical reactions, stuff like burning fuel or digesting your lunch, bonds between atoms break and form. The energy involved there is typically in the thousands of kilojoules per mole, and the mass changes are so small they're virtually undetectable, way down in the nanogram range. But look at nuclear binding energy. We are talking about billions of kilojoules per mole, and the mass differences are in the milligram range. The energy changes associated with nuclear reactions are vastly greater than anything we see in standard chemistry. It's just an entirely different league of power.
Part 3. The band of stability, mapping the quest.
Now, what's really interesting about this slide is that it acts as a geographical map of nuclear survival, because the truth is, not every nucleus manages this balancing act. This graph plots the number of neutrons against the number of protons for known nucleoids. See that blue zone? That represents the stable isotopes, the ones that have successfully balanced their internal forces. We call this the band of stability. All those green dots surrounding it, those are your unstable radioactive isotopes. They're trapped in dangerous territory and they must undergo spontaneous changes, decaying over time, to try and migrate into that safe blue zone of stability. And notice how the blue line isn't perfectly straight? We're going to explore why that is right now.
So there are actually some pretty fascinating structural rules that dictate this stability. It's definitely not random. Nuclei with certain numbers of nucleons are especially stable against decay. We call these magic numbers, numbers like 2, 8, 20, and 28. These create complete, highly stable shells within the nucleus, kind of like the stable electron shells you see in noble gases. If a nucleus has a magic number of both protons and neutrons, take helium-4 for example, with 2 of each, it's called double magic, and it is incredibly stable.
And looking back at our map, while lighter stable atoms maintain a nice 1-to-1 proton-to-neutron ratio, heavier atoms absolutely require an excess of neutrons. They just need those extra neutral particles to provide enough strong nuclear force to keep all those repelling protons in check.
Moving on to 4. Particles and nuclear equations, the mathematics of decay.
So how exactly do unstable atoms make this journey to stability? Well, when they decay, they emit radiation. Think of these emitted particles and rays as the essential vehicles of nuclear change. We have alpha particles, which are relatively massive, high-energy helium nuclei. We have beta particles, which are high-energy electrons just ejected straight from the nucleus. We have gamma rays, which, interestingly, aren't particles at all, but highly energetic electromagnetic radiation. And we have positrons. These are positively charged electrons, literally actual antimatter. When a positron meets an electron, boom, they annihilate each other, converting their mass entirely into gamma-ray energy.
Now, when we write nuclear equations to track these changes, we aren't balancing whole atoms like you do in normal chemistry, we're tracking the nucleons. But don't worry, there are still strict conservation laws. Step 1, the sum of the mass numbers, those are the top numbers, of the reactants must perfectly equal the sum of the mass numbers of the products. Step 2, the sum of the charges, the bottom atomic numbers, must also balance on both sides of the equation. No matter how violent or energetic the nuclear reaction is, these mathematical accounting rules are always obeyed.
Section 5. Modes of radioactive decay, vehicles to stability.
So, the crucial point is that the type of decay an atom undergoes depends entirely on where it sits relative to that band of stability we looked at earlier. Heavy nuclei, stuff with atomic numbers over 83, they often use alpha decay, spitting out a massive alpha particle to shed both mass and protons really quickly. If a nucleus has too many neutrons, it might undergo beta decay, converting a neutron into a proton and ejecting a beta particle, which shifts its ratio closer to stable. Conversely, if it's got too many protons, it might use positron emission or electron capture to convert a proton into a neutron. And gamma decay often just naturally accompanies these other modes, as the newly formed excited nucleus sheds excess energy to settle into a relaxed, stable state. And by the way, the kinetics of this whole journey, how fast an unstable isotope actually decays, is measured by its half-life. That's a consistent rate of decay unique to every single radioactive isotope.
And you know, this isn't just theoretical textbook stuff. We actively harness these specific decay modes for some incredible medical technologies. Take positron emission. This is the exact mechanism behind a PET scan at the hospital. Doctors introduce a radio tracer that emits positrons into a patient. As those positrons encounter electrons in the patient's tissue, they annihilate. They emit gamma rays that scanners then detect to create highly detailed real-time images of how organs, like your brain, are functioning. It's amazing. We use the fundamental rules of nuclear instability to diagnose and save lives. And understanding those precise half-lives I mentioned, that is exactly how we use radiometric dating, like carbon-14, to accurately determine the age of ancient artifacts.
And finally, Part 6, Transmutation and Nuclear Energy Human Intervention.
So what happens when humans decide to actively intervene in this microscopic battleground? Up to this point, we've really just talked about spontaneous radioactive decay, but we can also force these changes. Nuclear transmutation is the conversion of one nuclide into another by forcefully bombarding it with other particles. The great Ernest Rutherford actually achieved the first artificial transmutation way back in 1919. He fired high-speed alpha particles at nitrogen gas and converted it into oxygen and hydrogen. He literally created the first man-made nucleus, proving that we aren't just passive observers of nuclear chemistry, we can actually be the architects.
And this brilliantly illustrates how far we've taken Rutherford's idea. What you're looking at is inside the 27-kilometer tunnel of the Large Hadron Collider at CERN. To achieve modern transmutation, especially to synthesize massive artificial transuranium elements that don't even exist in nature, we need unimaginable amounts of energy. So, we use giant particle accelerators, like this one, packed with super-cooled electromagnets, to whip particles around a vacuum tube at nearly the speed of light before just smashing them into targets. This is exactly how we've extended the periodic table well past uranium, creating entirely new heavy elements like plutonium, americium, and seaborgium. Which leaves us with a pretty profound question to end on. If stars use the immense heat and pressure of nuclear fusion to build the natural elements of the universe, and we use massive accelerators to forcefully extend the periodic table right here on Earth, what is the ultimate limit to the new synthetic elements humanity can create? Are there undiscovered islands of stability out there among the super heavy elements just waiting for us to synthesize them? It's an absolutely thrilling frontier in our ongoing quest to decode the microscopic universe. Thanks so much for joining us for this explainer.